In this section, we're going to talk about confidence intervals for proportions. So let's review our empirical rule for our estimators. Our central limit theorem says the sampling distribution of all the possible sample proportions, p hat, will be approximately normal for big enough sample sizes, and the expected value of all those possible sample proportions will be equal to p, our population proportion, and the standard deviation, also called our standard error, will be equal to the square root of p times 1 minus p over n. But usually we don't know our population proportion, so we're going to estimate that with our sample proportion. So what all that means is we can apply the empirical rule to our estimate p hat. So we can say if this is our parameter, in our case it'll be our population proportion p. If we go out one standard error in either direction, that's going to be 68% of all the possible p hats. So all the possible values of p hat. And if we go out 2 standard errors, that's going to be 95% of all the possible values of p hat. And if we go out 3 standard errors, that will be 99.7% of all the possible values of p hat. And that's all centered around our actual population proportion p. So again, 68% of the time, our estimate p hat will be within about 1 standard error of the population parameter p. And 95% of the time, this is the one that we're going to really care about today, 95% of the time, our estimate will be within about 2 standard errors of our population parameter p, the population proportion. So we're going to say 95% of all of our possible sample proportions should be within about 2 standard errors of the population proportion. But 2 is just an easy number to memorize. It isn't the exact value you have to go to be within 2 standard errors, or isn't the exact value to be within 2 standard errors. Let's use R to find the exact z value for a normal distribution that would have 95% of the values in the middle. So what would we have to put into R to do this? If I have a normal distribution and I want to have 95% in the middle, let's change that to decimal, 0.095 in the middle. How much would I have in each tail? If I do 1 minus 0.95, that gives me 0.05, but that would be both tails. That's both tails. And if I wanted to find one tail, I would divide that by 2. So one tail is going to be 0.05 divided by 2, so 0.025. So I'd have 0.95 in the middle. I'd have to have 0.025 in the left and 0.025 in the right tail. And I'm looking for a z value that would do that would split it up. So I have 0.95 in the middle. Now remember, on our normal curve, it's symmetric. So whatever this value is here, it would be the identical value here. It would just be a negative value. So there's a few ways that we could do this. We could put it in R. So remember, if we know the area and we want to look up the z value, we're going to use a Q norm. So I'm going to do Q norm. And remember, Q norm tells me, or I have to put in the area in the left tail. So if I put in 0.025, let's see what that gives me. So if I put in 0.025, okay, into R, let's start a new script. So Q norm 0.025. That gives me negative 1.96. So that equals negative 1.96. So this value right here is negative 1.96. There's other ways I could put this in to R. I could have said, well, if I wanted this positive z value right here, I would have had to say, what's all of the area from here all the way over? That would be, if I added them together, that would be 0.975. So I could say, well, what's Q norm of 0.975? So let's try that. Q norm 0.975. That tells me it's 1.96. So that equals 1.96. So I know that this z value equals 1.96. Again, because it's a metric, if I looked this up and got negative 1.96 here, I would have known that this z value was positive 1.96. Okay. I could have also said, well, if I want this value, I know that there's 0.025 in the right tail. So I could have also said, what's Q norm of 0.025 and done my lower dot tail equals F, or I could have written out false. And when I type that in, it's going to give me 1.96. So no matter how I think about it, I can figure out that this z-value is 1.96. So instead of saying if that 95% of the time our estimate is within 2 standard errors, because that was easy to memorize, technically we'd have to say 95% of the time our estimate should be within 1.96 standard errors of the population parameter. So our next example, USU has 28,000 students. We know that about 11% of all the USU students are graduate students. So let's summarize this. When it says USU has 28,000 students, that sounds like an entire population. So that's the population. We know about 11% of all the USU students. So that sounds like it's a population proportion. So my population proportion is 0.11. That's my population proportion. Now, if we were to take a sample of 200 USU students, so we'd have a sample size of 200, what would we expect the sampling distribution of all the possible sample proportions to look like? So we've done this. This goes back to our sampling distribution, but this is setting us up to learn some new information. So first, what do you think the shape would look like? The shape would be normal. Okay. So we're talking about proportions. So our sampling distribution will be normal if n times p is at least 10 and n times 1 minus p is at least 10. So we'll say it. We have to check if they're both at least 10. So let's try that. So 200 times my population proportion 0.11 gives me 22, that's at least 10. And 200 times 1 minus 0.11, which gives me 178, that's also at least 10. Okay? So it is going to be normal, at least approximately normal. Okay? And the mean of all those possible sample proportions is just going to be equal to our population proportion, so that'll be 0.11. And the standard deviation of all the possible sample proportions, also called standard error, okay, is going to be equal to the square root of our population proportion times 1 minus p over n. And we actually know the population proportion in this instance, so we'll do 0.11 times 1 minus 0.11 divided by my sample size of 200. And then I take the square root of all of that. So that gives me 0.022. So that's what I'm predicting for my mean and standard deviation for all those possible sample proportions and the shape. Now, I actually simulated a sampling distribution for you. So here's my sampling distribution of all those possible sample proportions. You can see I marked where the population proportion of 0.11 is. It does look like it's under there. Okay, so it's 95% of the possible sample proportions should be within what interval? Well, we know 95% should be within 2 standard errors. Okay, but we also decided 2 standard errors wasn't the most precise, so it should be within the population proportion p plus or minus 1.96 times the standard error of p hat. And let's see what that interval actually would be. So we know my population proportion is 0.11 plus or minus 1.96 times the standard p hat on the last page. We just decided that was 0.022. So this gives me, first I will do the subtraction. So when I subtract, I get 0.067. And when I add it, I get 0.153. So 95% of all the possible sample proportions should be within this interval. And if you were to draw that out, it looks like from about here to about here on my graph. And yeah, that's probably about 95% of all those possible sample proportions. Okay. But now, here's the important part. If 95% of all those possible sample proportions, p hats, are within 1.96 standard errors of my population proportion, we could turn that around. So let's turn that around and say that p is within 1.96 standard errors of 95% of all the p's. Okay. What that means is here's this distance from here to here, this is plus or minus 1.96 times the standard error, is that distance. Well, if I don't know my population proportion and all I know is my sample proportion, let's say I got this sample proportion. If I got this sample proportion and I went out the same distance of plus or minus 1.96 times the standard error, does that include my population proportion? Yeah, that's within that range, would hit my population proportion. What if I picked another one, like say right here, and I went out that same distance of plus or minus 1.96 standard errors? Notice that interval would include my population proportion P. But what if I happen to get this sample proportion and I went out plus or minus 1.96 standard errors? Notice that does not contain my population proportion P. Okay. So my sample proportion I got was so far out in the tails that it is not actually within 1.96 standard errors of P. But anything from here to here that was originally within that 1.96 standard errors, any sample proportion I get, if I add 1.96 standard errors, that interval will contain my population proportion. And that's true for anything in this interval, which is 95% of all the possible sample proportions. Now, I want you to suppose that you didn't know that USU had 11% graduate students. So what we're going to do is find a confidence interval. We can find a 95% confidence interval for my population proportion P by doing my estimate, which is P hat, plus or minus 1.96 times the standard error of the estimate, so the standard error of P hat. So let's suppose we took a sample and we got a sample proportion of 0.10. Can you find a 95% confidence interval for the plausible values of P? So what I'm going to do is I'm going to take my estimate of P hat of 0.10 and I'm going to do plus or minus 1.96 times the standard error of P hat. Okay. But now here's the problem. We're pretending that we don't know that USU had 0.11. So I'm going to have to estimate that standard error with my sample proportion of 0.10. So we'll do 0.10 times 1 minus 0.10 divided by my sample size of 200, I believe. Now, this standard error right here, if I put that into my calculator, that's 0.0212. So if I was to rewrite this, it would be 0.10 plus or minus 1.96 times the standard error, 0.0212. So if I put it in my calculator and I do the subtraction first, I get 0.0582, and then when I do the addition, I get 0.142. So this is a 95% confidence interval for the possible values of P. So based on my sample, I would tell you that I'm 95% confident that my population proportion is between 0.058 and 0.142. Would I be correct? Yes, because my population proportion is 0.11. So my confidence interval of here are some possible plausible values of P is correct. It did actually contain my population proportion. So what if another person took a sample of 200 students and found that their sample proportion was 0.15? Let's find a 95% confidence interval for P for them. So they would take their population, their sample proportion of 0.15 plus or minus 1.96, and then they times it by their standard error. But we don't know what that is yet, so let's find it. So it'd be the sample proportion of 0.15 times 1 minus 0.15 divided by sample size of 200, and then you take the square root of all of that. So if I simplify that, it'd be 0.15 plus or minus 1.96. And when you calculate the standard error is 0.0252. So to put this in your calculator, you do 0.15 minus 1.96 times 0.0252. So that gives me 0.1012, and if I do the addition, so 0.15 plus 1.96 times 0.0252, That gives me 0.199. So here is a different confidence interval based on a different sample. So that confidence interval says we're 95% confident that my population proportion is between 0.101 to 0.199. And notice that my true population proportion of 11% is within that interval. So that interval was also accurate. But let's say another person took a sample of 200 students and found that p hat is 0.21. So let's find a confidence interval again. So we'll do 0.21 plus or minus 1.96 times, and we'll do the square root of 0.21, times 1 minus 0.21, divided by 200, and we put all of that inside a square root. Let's see, if I simplify that, it's 0.21 plus or minus 1.96 times, let's see, what was my standard error? 0.0288. So if I do the subtraction, I get 0.154, and if I do the addition, I get 0.266. So here's my 95% confidence interval. Now notice this does not contain my true population proportion of p equals 0.11. So what happened? What happened was I picked this value right here of 0.21, and it was so far away from p to start with that the confidence interval doesn't actually contain my true proportion of p. Now, it's very unlikely to get a sample proportion way out here. Most of our sample proportions are in the middle, and they give us accurate confidence intervals. But occasionally, we could pick a sample that is just so unlucky, it's so far out on the tails, that our confidence interval does not actually contain our population proportion. So, let's look at our theory here. Every different sample would give us a different sample proportion, p hat. So that means every sample gives us a different 95% confidence interval for our population proportion p. If our sample proportion p hat happens to be in the middle within that 1.96 standard errors of the population proportion p, then the confidence interval will contain p. So that's for all of the values that are here in the middle. They're so close to our population proportion that their confidence interval will contain the population proportion p. But if our sample proportion p hat happened to be one of the ones that was in the tails, farther than 1.96 standard errors, then the confidence interval will not contain p. So that's if I pick a sample proportion from the tails, just by bad luck, then their confidence interval is just going to be so far away that it won't actually contain p. What that tells me is that 95% of all the possible sample proportions would give us a confidence interval that contains the population proportion p. But that means that 5%, okay, if 95% contain p, 5% of all the possible sample proportions would give us a confidence interval that does not contain our population proportion p. So we can use an applet to simulate what could happen if we took many, many different samples and found confidence intervals for each sample. So here's the link for our applet. When I come to the applet, I put in my population proportion. This was written for a different textbook. They used a different symbol. But it's just saying we have a population proportion of 0.11. We have a sample size of 200. And if I find one interval, here, notice this green line right here. The dot in the middle is my actual sample proportion, and then you can see the confidence interval. So the confidence interval went from here to here, and you can see that it did contain my true population proportion of 0.11. If I draw another sample, notice I got a different sample mean, and a different sample proportion, and my confidence interval changed a little bit, but it still contains my true population proportion at 0.11. If I take a different sample, it moved again. And every time I take a different sample, notice that my confidence interval moves a little bit. But most of them, so far, they've all been containing my true population proportion. What if I take a few more samples at a time? So here are 10 different sample proportions, the little black dot each time, and then each one, they added 1.96 standard error, so you can see the confidence interval. And most of these confidence intervals contained my true population proportion of 0.11, except for there was one right here. This sample proportion was so far away that its confidence interval does not contain my true population proportion. If I do this 100 times, Notice most of my intervals will actually contain my true population proportion, but some of them don't. So far, for all of the ones that I've done, about 93.6% contained my population proportion. And if I did this many, many more times, okay, many times, you'll see that the proportion that, or about 95% of all of my possible intervals will contain my population proportion P. So each one of these little lines is a different confidence interval from a different sample. We can see that overall about 95% of all of the intervals will actually contain our population proportion of 0.11. So every different sample proportion gives us a different confidence interval. But if we looked at thousands of possible samples, 95% of the very samples give us a confidence interval that actually contains the population proportion P. And that's why we're going to call it a 95% confidence interval.